Welcome back, everyone. So in this video, we're going to talk about intersecting polar graphs. So we're going to look to see where these polar equations are going to intersect, specifically on a polar graph. So we're just going to dive right into number one. You can see my little duck constantly getting in the way, or goose, or whatever it is. So I will say this lesson is actually going to be much easier after you do 7.3. I know this is technically part of 7.2. But if you do 7.3 first and then come back and do these problems, it's actually going to be much easier, much quicker, because you'll get some of the graphing components. So just kind of starting off. So the first equation we have over here is going to be r equals 5, and then we have r equals 5 plus 5 sine theta. So I'm going to do these problems under the assumption that you've already done 7.3, so that will help me with kind of the graphing aspect of these. So looking at this first equation, r equals 5, this is just going to be a circle centered at the pole with a radius of 5. So I'm going to start with graphing this circle. And then your next graph over here is going to be a cardioid. And then because I have a positive sine equation, that tells me the cardioid is going to open up. So the components of a cardioid equation, my a value over here is going to tell me either the x or y intercepts depending on which way it faces. Because we have a positive sine equation and it opens up, that tells me that this cardioid is going to have x-intercepts at 5 and negative 5. And then because it's a cardioid, it is going to pass through the pole. So I know it's going to pass through this point right here. And then to find the length of the cardioid in the direction that it opens, you can do 5 plus 5 or the a plus b, which means it's going to go all the way to 10. And then I'm going to draw my graph. I'm going to start with a circle, then extend it. And then I'm going to use my partial eraser so that I can get rid of this bottom segment. Hopefully that did it. There we go. Then I'm going to finish off the cardioid shape, and it's going to go something like this. Go away. So when you're looking at your intersecting graph, or your intersecting polar graphs, you're going to look to see what those coordinates are, because you're going to answer these by giving me coordinates. Because in the directions up here, we say find all points. So your points are going to be in the form of r comma theta. So over here, if you look at your graph, you're going to have just 2 points of intersection. So algebraically, you want to justify what those points are going to be. So what I'm going to do to find those points algebraically is I'm going to do essentially a system of equations. So I'm going to do a system of equations by substitution. So I'm going to set r equal to r. So I'm going to take my cardioid equation, which is 5 plus 5 sine theta, and I'm going to set that equal to the circle, and then just solve it like you would a typical algebra 1 equation. So subtract 5 on both sides. So that's going to give you 5 sine theta, which is going to be equal to 0. And then you're going to divide both sides by 5. So that's going to give you sine theta is equal to 0. Now it just turns into a unit circle problem. So you want to know on the unit circle, where does sine of theta equal 0? So that's going to happen at 0 and pi. Go away. So the next thing, we have our theta value, but now you still need to find and plug it in to see what your r value is going to be. So we can see it over here from the graph, but you may not have a graph readily available, so you do want to be able to find these algebraically. So what you're going to do is you're going to take your theta values and you're going to plug them in to your system. Now, you can plug them in hypothetically to either equation. It doesn't matter which one you do, but if you look up here on the r equals 5 equation, then there's no theta value to plug it in, so you can only plug it in into the cardioid equation here. Go away. So when I plug in, so I'm going to do f of 0, and that's going to equal 5 plus 5 sine of 0, which is going to give me 5 plus 5, and then sine of 0, which is going to be 0. So 5 plus 5 times 0 is just going to give you 5. So my coordinate in which this is going to happen, it's going to be a distance of 5 from the pole in the direction of 0 radians. So this would be 5, 0. So that would be the first point. Now I still need to plug in the second point over here, or the second theta value. Now, it should work out to be the exact same value as your original value, because if you do sine of both of these values, they're going to get the same value. So I'm still going to algebraically show it, but depending on your steps, you may not need to. So 5 plus 5 sine, go away, of pi. What is going on? Go away. So this is going to be, let's go down here. 5 plus 5 sine of pi, which is going to be 0. So we get the same thing as we did before. The only thing that's different is the direction that we go in. So this would be 5 in the direction of pi. So that's going to be your 2 points over here, 5 in the direction of 0, and then 5 in the direction of pi. So for your final answer, you're just going to write those 2 coordinates. Go away. There we go. So the very first one here, this is kind of your standard run-of-the-mill problem. So as we go on, we're going to get into some more complex problems. So we're actually going to jump down to number 9 next. So number 9, go away. So we have r equals 3 minus 6 cosine theta, and then r equals 4 minus 4 cosine theta. So when I look at these values, I see my a value in this first equation is 3, and my b value is 6. When I do my ratio of my a over my b, that means we're going to have 3 over 6, which is going to be equal to 1/2. Now, because that's equal to 1/2, it's less than 1. That means we're going to have a Limiçon with an inner loop. Okay, and then my second equation here, if your a and your b value are equal, that tells me we're going to have a cardioid. So I'm going to go ahead and graph these. So I know for this Limiçon with the inner loop, it's a negative cosine equation, so it's going to open left. And then the length of my shorter loop is going to be the absolute value of 3 minus 6, which is going to be 3. So I'm going to go towards the left, so I'm going to go to the third circle for the inner loop. And then for the outer loop, I'm going to do 3 plus 6. So that's going to go all the way to 9. And then because it opens left, we're going to have y-intercepts, and that's going to be at my a value, which is 3. So I'm going to go to the third circle up and third circle down. And then my Limiçon with the inner loop, algebraically, if you want to check to see if an equation is going to go through the pole, so what I like to check is I reference the rectangular equation, so to speak. So what I like to do is the midline, go away, plus or minus the amplitude. So as you hopefully remember, so that's going to be the equation a sine, go away, b parentheses x minus c plus d. So I'm going to be referencing my d value plus or minus my a value. So this is your d plus or minus a from your trig equation. So that's just kind of a quick little recap. So whenever you do your equation or your midline plus or minus amplitude, you're going to generate 2 values. You're going to have a value that's d minus a, and then you're going to have a value that's d plus a. And what you're checking is you want to see, is 0 included in the interval d minus a comma d plus a. If 0 is included, that means the pole is a point on that graph. If 0 is not in that interval, that means the equation does not pass through the pole. So we're going to check to see if 0 is included. Go away. I know I can turn that feature off, but it's also cute. So anyways. So over here, when I check the Limiçon with the inner loop, I'm going to check to see if this equation is going to pass through the pole. So I know my midline is going to be 3. I know my amplitude is going to be 6. We're going to disregard this negative here because that's just going to tell us the direction. When you're taking the values to do d plus or minus a, you're going to take the absolute value of those individual values. Okay, so when I check the pole, I guess we'll just do this over here. Oh my god, go away. So I'm going to do my d value, which is 3, plus or minus my amplitude. So that's going to do 3 minus 6, which is going to be negative 3. And that's going to go until we get to 3 plus 6, which is positive 9. So the values from negative 3 to positive 9, 0 is included in that interval, which means the pole is a point. So that means I can go ahead and just put a point at the pole. So I'm going to go ahead and draw my graph. So I'm going to start with a circle. Extend. Partial eraser. Get rid of that. Then I'm going to draw my inner loop. See if I can do this. Close enough. Okay, so there's my Limiçon with the inner loop. Now I want to draw my cardioid. So for my cardioid, go away. So that's going to be cardioid opening left. I'm going to have y-intercepts at 4. So 1, 2, 3, 4, let's see if I can count, 4 and 4. And then let's check the pole. So for the cardioid, that's going to be 4 plus or minus 4, which means my values are going to be from 0 to positive 8. And because 0 is included in that interval, what that tells me is the pole is going to be a point for the cardioid. Okay, so now I'm going to have a point here at the pole, and then it's going to open left, and it's going to go all the way to 8 when you add those two A and B values together. So that's going to go to here. So when I draw my cardioid, that's not a circle. There we go. Partial, goodbye, goodbye. This is the one that kind of looks like a butt. There you go. So when you look at your graph here, we're looking to see where it intersects. So I can see we're going to intersect about over here. We're going to intersect at the pole, and then we're going to intersect somewhere over here. So I hand drew these, so it's probably not going to be entirely accurate, but you want to get an idea of how many points of intersection you're going to have. So now that I have my graph drawn, I know to expect 3 points of intersection. So I already got the pole when I looked over here. So I know 0, 0 is going to be a point. Now I want to solve these algebraically. So I'm going to do 3 minus 6 cosine theta, and then that's going to equal 4 minus 4 cosine theta. So now when I solve, go away. So I'm going to add 6 cosine theta on both sides. And I'm going to go ahead and just do 2 steps in one. I'm going to go ahead and subtract 4 also. Okay, so when I do this, then we're going to have -1 is equal to 2 cosine theta. Then you're going to divide by 2 on both sides. Go away. So cosine theta is going to be equal to -1/2. Now it just turns into a unit circle problem. So this is going to happen at theta is equal to 2 pi over 3. And also, 4 pi over 3. That's a 3. So next, we found the theta values. Now you need to plug in the theta values so you can see what the R value is going to be. Now, in this case, you can plug in your theta value into either your Limiçon with the inner loop, or you can plug it into the cardioid equation. It's not going to matter which one. Personally, I usually like to go to the cardioid equations, but that's just me personally. So I'm going to plug in, not R, let's do F. So I'm going to do F of 2 pi over 3. So that's going to be 4 minus 4 cosine of 2 pi over 3. So when you get here, 4 minus 4, then cosine of 2 pi over 3, you already know what that value is based on what you did like 5 seconds ago. So hopefully you get that value right. If you get that value wrong, there's not much I can do. Okay, so as you continue here, so we're going to do 4 minus 4 times -1/2. So that's going to turn into 4 plus 4 times 1/2. So that's going to be 4 plus 2, which is going to turn out to be 6. So when I write my coordinate, this is going to be a distance of 6 from the pole in the direction of 2 pi over 3. Okay, and then I'm going to do the same thing. You shouldn't need to plug in the second one because that's going to give you the same idea, but I just want to show you algebraically. So this would be 4 minus 4 times -1/2, which of course is going to give you 6. So this is going to generate the point 6, 4 pi over 3. Okay, so your 3 points of intersection that you're going to have 6 in the direction of 2 pi over 3. You're going to have 6 in the direction 4 pi over 3. And then we're also going to have the pole, which is going to be 0, 0. Now, I don't have a preference or really care if you write 0, 0. You could also just write the pole. On assessments, you could expect either one of those to pop up. So I don't care whether you write 0, 0 or pole. Either one is fine. Okay, moving on. Now we're going to come back up to number 8. So looking at your equations here, so I've got r equals 2 plus 14 cosine theta, and then we've got 6 plus 6 cosine theta. So looking at these, I can see my ratio of my a over b is going to be less than 1, so this is going to be a Limiçon with the inner loop. And then over here, we're going to have a cardioid since those a and b values are equal. So next thing, So I'm going to try to graph these, but if you want, you can do a scale. I'm not going to worry about a scale because, as you see, this 14, that's going to be a bigger number than what your graph is really going to allow. We only go up to 10 on this polar graph, but I'll make adjustments as needed. So I'm actually going to start with the cardioid. Cardioids to me are much easier. So it's going to open right since we have a positive cosine. So that tells me we're going to have y-intercepts at 6 and 6, or 6 and negative 6. And then if I check the pole for the cardioid, so I'm going to do my d value plus and minus my a value. So that'd be 6 plus or minus 6, which means that's going to go from 0 to 12. So 0 is included in that value, which means the pole is going to be a point of intersection. Or not really a point of intersection yet, but I know that this cardioid is going to pass through the pole. So I'm going to go ahead and put a point at the pole. And then I know that we're going to have a point at 12. So I'm going to kind of just guesstimate. So I'm going to put it over here. Perfect. Let's try to get it on the actual grid. Okay, extend. So once again, I'm drawing these by hand, so it's not going to be entirely 100% accurate, but this will at least give me an idea of how many points of intersection I'll have. Terrible. Trying to maintain as much curvature as I can. Perfect. Okay, now for the next equation, now we're going to do the Limiçon with the inner loop. So we have positive cosine, so it's going to open to the right. We're going to have a short loop, and I'm having a stroke. The inner loop is going to be a length of 12 when you do the absolute value of 2 minus the absolute value of 14, and then take the absolute value of that. So that's going to go right here. And then we're going to have intercepts at, what are those values? Nope. Okay. My larger loop is actually going to be at, where is it? 16, which that's going to be pretty massive. So my points of intersection, let's see. That's not a circle. That'd be, let's see, 12, 13, 14, 15, 16. Do as I say, not as I do. That's going to be about right there-ish. Okay, so that would be the outer loop, and then I need to get rid of this point and this point. Get rid of this part. So I'm going to be able to pass through the pole, because when I check the pole over here, so I'm going to do the d value, so 2 plus or minus 14, which that's going to give me negative 12, going until we get to 16. So 0 is included in that interval, so that means I am going to pass through the pole. So over here, pass through the pole, and then I'm going to go to the inner loop, which is going to be way over here, and then we're going to come back around. So when I look at my graphs here, I'm going to have points of intersection about over here, here at the pole, and then down here. So we're going to have 4 points of intersection. So I can already see that the pole is going to be one of my points of intersection. Now we're going to algebraically solve for the other points. Go away. I missed. So this is going to be 2 plus 14 cosine theta, and that's going to equal 6 plus 6 cosine theta. Go away. So when I solve, so subtract 6 cosine theta on both sides. Then I'm also going to go ahead and subtract 2. Go away. So over here, that's going to leave me with 8 cosine theta. That's going to equal 4. Then divide by 8 on both sides, so that's going to leave me with cosine theta is going to equal 1/2. So when I do that, we're going to have cosine theta is equal to pi over 3 and 5 pi over 3. So when I look over here on my graph, this is going to be about pi over 3. This is going to be about 5 pi over 3. So once again, drawing it by hand, so it's not going to be entirely accurate. But the graph is really just to kind of give you an idea of how many points of intersection you're going to have. Now, next thing is we're going to plug in these theta values. So once again, it's not going to matter which one you plug it into. So I like to use the cardioid. So I'm going to do f of pi over 3. So that's going to be 6 plus 6. And then cosine of pi over 3. So when I plug in, or when I sub in, so that'd be 6 plus 6 cosine pi over 3, which is going to be 1/2. Which is going to give me 6 plus 3, which is going to give me 9. So that means my coordinate here is going to be 9 in the direction of pi over 3. Okay, and then same idea for 5 pi over 3. Those have the same cosine value, so that's going to yield the same output value. So I'm just going to skip down to the coordinate. So this is going to be 9 in the direction of 5 pi over 3. Which, based on my drawing, it's almost there. Okay, so we know that the coordinate 0, 0 is going to work based on when we check for the pole up here. And then I got these 2 points over here based on algebraically solving. Now, if you notice, we did not get this last point over here. So in order to get that last point, what you're going to want to do is you're looking for a reflected point. So because you're looking for a reflected point, what you're actually going to end up doing is you know that this is going to go either in the direction of 0 radians or it's going to go in the direction of pi radians, but have a negative r value. So what I'm going to do is I'm actually going to plug in 0 and pi into both of these equations and see if it's going to yield the same point. So what I'm going to do, so I need to plug in theta equals 0 and theta equals pi. So when I do this, so I'm going to do f of theta. We're actually going to start with the Limiçon with the inner loop. So when I plug in, I'm going to do 2 plus 14 cosine of 0. So when I do that, that's going to be 2 plus 14, go away, which is going to give me 16. So that tells me this point here, go away, is going to be 16 in the direction of 0. Now I want to plug in pi and see what that point's going to give me. So when I plug in, we're going to get 2 plus 14, go away, cosine pi. So that's going to be 2 minus 14, which is going to give me negative 12. And then that's going to give me the point, negative 12, in the direction of pi. Okay, so next I'm going to do the cardioid. So I'm going to do f of 0. And that's going to be for the 6 plus 6 cosine equation. So 6 plus 6 cosine 0. So that's going to be 6 plus 6 times 1, which is going to be 12. Go away. So that's going to be 12 in the direction of 0. And then I'm going to plug in pi. So 6 plus 6 cosine pi. So that's going to be 6 minus 6, which is going to be 0, which means that's going to be 0 in the direction of pi. So what I'm going to do next is I'm going to look at these 4 points, or rather these 2 sets of points. I want to see if any of these points actually represent the same point. So if you look, we have 12 in the direction of 0 and negative 12 in the direction of pi. Those are actually going to generate the same point. And that is what's going to give you this point right here. So that is going to be your other point of intersection. So what I recommend that you do is you're going to look to see what point on your graph that you did not get algebraically, and you want to see in what direction that point is in. So I see that this is going towards 0, or it could be going towards pi if it's a reflected r value. So that's why I plugged in both 0 and pi. So that is what gave me these 2 points, which end up being the same point. So my solutions for this problem, so we're going to have the points 9 in the direction pi over 3. We're going to have 9 in the direction 5 pi over 3. We're also going to have the pole, which is going to be the point 0, 0. And then for your last point, which is that reflected point, then we're going to have the point, and you can write it a couple different ways. You can either say 12, 0, or you can say negative 12 in the direction of pi, since those technically represent the same point. So I would accept those 4 coordinates. Now, a very common, what's the word? One thing I do want to make sure I point out, when you're considering intersecting polar graphs, we do not consider the rectangular graph. Okay, so meaning, I'm actually going to show you with number 8, because that would be a perfect example. So if I go over here to Desmos, so I'm going to go in the top right corner, click on that wrench, go to a polar graph. Then over here, I'm going to type in my equation. So I'm going to have r is equal to 2 plus 14 cosine theta. So that's going to give me my Limiçon with the inner loop. And then I'm also going to type in the equation r is equal to 6 plus 6, equals 6 plus 6 cosine theta. So I can see the polar graphs, but now I also want to show you the rectangular graph, because we're going to see that we are going to intersect at 2 places. So I'm going to go back to my rectangular graph. So I'm going to type in y is equal to 2 plus 14 cosine x, and then y is equal to 6 plus 6 cosine x, not theta, x. So I'm going to come over here back to the wrench. I'm going to go from, let's just go from 0 to 2 pi. Then turn the x-axis into radians, so I'm going to do by pi. So let's adjust the y-axis. Let's go, say, negative 20, and then positive 20. So when I look at the rectangular graph, I see that we only actually intersect twice. So that's why algebraically we only got the pi over 3 and the 5 pi over 3. However, right here we get the pi comma 0, but then we also get pi comma negative 12. So this is actually where those points are going to overlap on the polar equation. So they don't intersect rectangularly, but it doesn't mean that they're not going to be a solution on a polar graph. So that's why over here, when you're looking at the intersection of the polar graphs, you're not going to actually consider the rectangular graph. It's not going to give you all the points of intersection. So you still need to consider the different techniques and schematics for a polar graph, because we are not going to follow the same techniques for a rectangular graph. So that point over here, even though it's a reflected point on a polar graph, they still intersect at that point. All right, so that being said, I would invite you guys to pause here, try number 10. But I'm going to keep going. Okay, so looking here. So for this first equation up here, we've got 2 minus 3 sine theta. So this is going to be a ratio of 2 over 3, which means it's going to be a Limiçon with the inner loop. We have a negative sine equation, which means it's going to open down. And then I'm going to have x-intercepts at 2. So 2 and negative 2. It's a Limiçon with the inner loop, so it is going to pass through the pole. I'll show that algebraically here in a second. And then to find the length of the inner loop, I'm going to do the absolute value of 2 minus absolute value of 3, and then take the absolute value of that, which is going to be 1. And then to find the length of the outer loop, it's going to be 2 plus 3, then absolute value of that, which is going to be 5. So start with my circle. Extend. Then get rid of. Ta-da. Close enough. Okay, so there's my Limiçon with the inner loop. Now, for the next part, we're going to have 6 plus 5 sine theta. Now, if I do my ratio 6 over 5, that's going to be bigger than 1. So because it's bigger than 1 but less than 2, that tells me we're looking at a dimpled Limiçon. So what that tells me, actually here, let's actually do the pole. I'm going to show the pole first. So when I check for the pole, so we're going to do the Limiçon with the inner loop. So I would do 2 plus or minus 3, which tells me my values are going to oscillate between negative 1 and 5. So 0 is included in that interval, which means the Limiçon with the inner loop is going to pass through the pole. Now, if I check the second equation, I would do the midline plus or minus the amplitude. So 6 plus or minus 5, that's going to give me values of 1 to 11. So this is not going to pass through the pole. So that means the pole cannot be one of my solutions. So a dimpled Limiçon, hopefully if you know from 7.3, is not going to pass through the pole. Okay, so for your dimpled Limiçon, what's going to happen, we're looking at the x-intercepts, which are going to be the first value, your a value, which is going to be 6. So I'm going to have x-intercepts at 6 and -6. And then it's going to go in the length of a plus b, which is going to be 11. So it's going to be a little off the graph, just a smidge, which is okay. And then for the dimpled Limiçon, you're going to actually go the opposite direction that it opens, and you're going to do the a value minus the b value. So it's going to open 1 in the opposite direction. So down here, when I draw my dimpled Limiçon, oops, it's off just a smidge, trying to line it up as much as I can. Of course, that's not going to be lining up as much as I want it to be, but that's okay. Okay, so now let's get rid of this, get rid of this. So when I do my dimpled Limiçon, it's going to be shaped kind of like a cardioid. It's just not going to pass through the pole. So it's going to look something like that. So what I can tell from here, when I draw this by hand, we're going to have 1, 2, 3, go away. We're going to have 3 points of intersection. So looking at the graph, I can see we're going to have another reflected point right here on the inner loop and the edge of that dimpled Limiçon. So algebraically, I should be able to get these 2 points, but I'm going to have to do that reflected point over here to get the third point. So let's go ahead and do the algebraic steps to find those 2 points. So I'm going to do 6 plus 5 sine theta, and then set that equal to 2 minus 3 sine theta. Okay, so when I solve algebraically, so I'm going to add 3 sine theta on both sides. And then I'm going to also go ahead and subtract 6 on both sides. Go away. Okay, so when I do this, that's going to give me 8 sine theta. And then that's going to equal -4. Math is hard. Okay, then divided by 8, so that's going to give you sine values of -1/2. And then on the unit circle, that's going to give me values of 7 pi over 6 and 11 pi over 6. Listen. So that's going to be approximately in the direction that we have these 2 values over here. So that checks out. So once again, now we're going to just plug in those theta values. So I'm going to use the top equation. The numbers are a little bit smaller. So I'm going to do f of 7 pi over 6. So that's going to be 2 minus 3 sine 7 pi over 6. All right, and then what's going to happen? So 2 minus 3 sine of, excuse me, sine of 7 pi over 6 is going to give me -1/2. So 2 plus 3 halves, which is going to give you 7 halves. So yeah, that kind of checks out because this is not going to be a pretty point over here. Now there's that one. So that fraction kind of checks out. So that tells me, go away. So that tells me this coordinate here is going to be 7 halves in the direction of 7 pi over 6. And then the next point should also be 7 halves, comma, 11 pi over 6. But when I check it, so 2 minus 3 sine 11 pi over 6. Go away. So 2 minus 3 times -1/2, which is also going to give you 7 halves. So just like I said, so this is going to be 7 halves, comma, 11 pi over 6. Okay, so we have those 2 points. Now I need to check where that third point is going to be. So that third point is going straight up or straight down. So I need to plug in and check pi over 2 radians, or it could be going straight down. So I need to plug in and check 3 pi over 2 radians. So I'm going to do those 2 values kind of like what I did over here, and we're going to see what points are going to be the same. So down here, so what I'm going to do is, go away. So I'm going to plug in theta equals pi over 2. And we're also going to plug in 3 pi over 2. Go away. So for the first equation, I'm going to look at the Limiçon with the inner loop. So I'm going to do f of pi over 2. And then that's going to be 2 minus 3 sine pi over 2. So that's going to give me 2 minus 3, which is going to give me negative 1. So I'm actually going to put you back up here. Go away. So this is going to be a point, negative 1 in the direction of pi over 2. So if I reference my graph, that's actually the point that I wanted, because if it was a positive one, then it would be up here. So likely that's actually the point that I want. So now I'm also going to check 3 pi over 2, even though this kind of already gives me a clue that this is not the point that I'm going to want. So 2 minus 3 sine 3 pi over 2. So that's going to be 2 minus 3 times negative 1, which is going to be 5. So that means we're going to go 5 in the direction of 3 pi over 2. So yeah, that's not the point that we want. So now I'm going to check the dimpled Limiçon. So I'm going to do f of pi over 2. Okay, so one thing I also just noticed, my notation is not necessarily the best on this. So really, if I want to be a little bit more technical, I could say this is going to be R1 and R2. So really down here, let me kind of fix this a little bit. I'm going to say R1 of pi over 2. That way I'm being a little bit more technical and a little bit more precise in my notation. And then R2 of 3 pi over 2. Should have did that on number 8 as well, but it's okay. Better late than never, I guess. Okay, so, whoops, that would be R1. So now I'm going to do R2 of pi over 2. So I'm going to take the second equation, which is going to be my dimpled Limiçon. So when I plug in, so this is going to be 6 plus 5 sine pi over 2. So when I do this, this is going to be 6 plus 5 times 1, which is going to be 11, which that's going to generate the point 11 in the direction pi over 2. Which that's not like any of those other points, so that means I'm going to want 3 pi over 2 for the dimpled Limiçon. So when I plug in, so 6 plus 5 sine 3 pi over 2. Wow, my handwriting is so bad, I'm so sorry. Okay, so this is going to be 6 plus 5 times negative 1, so 6 minus 5, which is just going to give me 1, which means I'm going to want to go 1 in the direction of 3 pi over 2. So if you kind of think back to 7.1 when we were just talking about polar coordinates, well, hopefully you'll see these are the same point. These points are going to match. So that is going to generate this point over here. Okay, so that's going to be our third point. So your 3 points of intersection. So we're looking at 7 halves in the direction of 7 pi over 6. We're also looking at 7 halves in the direction of 11 pi over 6. Go away. And then we're also going to have the point negative 1 comma pi over 2. Or you could write 1 in the direction 3 pi over 2. I would accept either one of those points. You only need to write the 3 points. If you want to write all 4 of those points, that's fine. Just make sure that when you're writing these points down here, you can say or. Because if you write them separately, then that tells me that you don't know that they're the same point. So you have to make that distinction on your assessment that you know that those represent the same point. Because I would count off if you give me technically those 4 coordinates. You have to tell me that these represent the same. Okay, so these are some really good kind of general run-of-the-mill problems. I do want to do one of the more spicy problems, I guess I could say. So I'm actually just going to start number 11. I'm not going to do it in its entirety because I just want to show you some of the kind of advanced schematics that can kind of go into this one. So for this one, so we have r equals 6 cosine 2 theta, and then we've also got r equals 6 sine theta. So based on the equation setup, this tells me this is going to be an even rows. And because we have an even value, we're going to double that number to get the number of petals. And then because it's cosine, that means the petal is going to be symmetric about the x-axis. So that tells me my general shape is going to have a length of 6, then go to the pole, then go down, back to the pole, then back over here, back to the pole, back up, back to the pole, and then back over here. So your rose is going to look something like that. Terrible, but you get the idea. And then over here, we have 6 sine theta. So this is just going to be a circle that opens up, and it's going to go 6 in the direction of pi over 2. So it's going to be a circle kind of like that. So we're going to look for the points of intersection based on those two graphs. Okay, so with this, trying to think, where do I even want to start? Let's actually start with algebraic steps. So I'm going to do 6 cosine 2 theta, and I'm going to set that equal to 6 sine theta. Now, if you look here, we have a double angle value over here on the left side, so we actually need to bring back identities. So I know from identities that a double angle for cosine is going to be the same as cosine squared theta minus sine squared theta. And then that's going to equal 6 sine theta. Go away. Now, over here, if you look on the right side, notice that we're going to have that sine ratio over here, and then we have another sine ratio over here, but then we have this cosine value here. So it's really going to be hard to solve this until we get everything in terms of the same trig ratio. So what that tells me is I'm actually going to change this cosine squared theta into terms of sine using more identities. So there's also variations of your double angle cosine that you could have just went straight to your sine ratio. But just in case you want to go step by step, or if you don't remember your trig ratios, that's fine. So I'm going to go ahead and do trig identities. I'm going to change cosine squared theta into terms of sine. And that's going to be 1 minus sine squared theta. And then we still have that minus sine squared theta. And then that's going to equal 6 sine theta. So when I rewrite, so this is going to be 6 parentheses 1 minus 2 sine squared theta. And that's going to be equal to 6 sine theta. So if you remember your trig identities fairly well, you can just go from this top line straight down here if you remember that this is also a variation of the double angle identity for cosine. Okay, so next I'm going to divide both sides by 6. So get rid of that, get rid of that. So we're going to be left with 1 minus 2 sine squared theta, and then that's going to equal sine theta. And then what I'm going to do next is I actually am going to move my entire left side to the right side. So doing that, I'm going to subtract 1, and then I'm going to add 2 sine squared theta. So add 2 sine squared theta. Now doing this, we can't combine any like terms, so this is just going to leave us with 2 sine squared theta plus sine theta minus 1. And that's going to equal 0. So hopefully based on this setup, you can kind of gather what we're about to do next, and that is going to be factoring. So you can do a substitution. You can say n is equal to sine of theta. If you want to, you don't have to, or you can just factor how it is. I'm just going to leave it and factor it how it is. So when I split the middle, so I'm going to do 2 sine squared theta. I'm going to do 2 times negative 1, which is going to be negative 2. Factors of negative 2 that add up to a positive 1. So I want positive 2 and negative 1 sine. So I'm going to do positive sine theta minus sine theta. And then minus 1. And that's going to equal 0. And then when I do grouping, we're going to be left with 2 sine theta. Go away. And that's going to leave me with sine theta plus 1. And then in the second group, we're going to take out a negative 1, and that's going to leave you with sine theta plus 1. I don't want to spend too much time on the factoring aspects. Okay, so then we have sine theta plus 1, sine theta plus 1. Those are the same. We're good to go. I'm going to factor that out. So sine theta plus 1. And then when I factor that out, we're going to be left with 2 sine theta minus 1, and that's going to equal 0. So now what you're going to do is you're going to split and solve. So I'm going to take this left equation over here, solve, and then I'm going to take the right equation over here and solve. Move. Don't honk at me. So this is going to be, not 2. So this is going to be sine theta plus 1 equal to 0. So when I solve, we're going to get sine theta is equal to negative 1, which on the unit circle, that's going to happen at 3 pi over 2. And then over here on the right side, we're going to get, I can't write, 2 sine theta minus 1 is going to equal 0. Go away. which is going to give us sine theta is equal, go away, to 1/2, which on the unit circle, that's going to give us pi over 6 and 5 pi over 6. Okay, so now that we have those values, now we're going to plug them in to our equation, and we're going to see what the corresponding r value is going to be. So once again, you can plug it into the rows equation, or you can plug it into the vertical circle equation. The vertical circle equation is going to be easier, so I'm just going to use that one. So when I plug in, so I'm going to say, let's make sure I use proper notation. So I'm going to say R1 and R2. So I'm going to plug it into R2. So I'm going to say R2 of 3 pi over 2. So that's going to be 6 sine 3 pi over 2. And that's going to be 6 times -1, which is going to be -6, which means that point is going to be -6 in the direction of 3 pi over 2, which that will be the same as the point +6 comma positive pi over 2. So now I'm going to plug in the pi over 6 and the 5 pi over 6. So R2 of pi over 6. So this is going to be 6 sine of pi over 6. So sine pi over 6, which is 1/2. So that's going to be 6 times 1/2, which is just going to give me 3. So this is going to generate the point 3 in the direction of pi over 6. And then when I also plug in for the other point, so we're also going to have 5 pi over 6. So that's going to generate the same point that we just did for pi over 6. So I want 5 pi over 6 here. So 6 times 1/2, which is 3. So that's going to give me the point, go away, 3 in the direction of 5 pi over 6. Okay, so we have those 3 points, but I do want to go ahead and graph these equations just to make sure that I've accounted for all my points. So over here, I'm going to do this, I say quickly, but hopefully it'll be still informative. So I'm actually going to start with the vertical circle. That's just going to be a circle with a diameter of 6 going upwards. So starting at the pole and then going up to the 6th concentric circle. Okay, and then for the graph of the rows, this one is going to be a kind of a recap of before. So when I graph roses, I like to start with a period. So that's going to be 2 pi over whatever your b value is, which in this case is going to be 2 pi over 2, which is just going to be pi. And then when I get the period, I'm going to look for the spacing. And this is what I'm going to count in my table by. So I like to do the period divided by 4. Listen. So that means in my table, I'm going to count by pi over 4. So when I make my table over here for the rows, it's going to be some r theta. My theta values, I'm going to count by pi over 4. So I'm going to start at 0, pi over 4, then 2 pi over 4, which is pi over 2, then 3 pi over 4, and then 4 pi over 4, which is pi. And then I'm going to keep going so you can kind of see a pattern. And then 5 pi over 4, 6 pi over 4, which is 3 pi over 2. And then 7 pi over 4, and 2 pi, which is 8 pi over 4. So what I'm going to do is I'm going to plug in these theta values into the rows equation. So when I plug in 0, this is going to be 6 cosine 2 times 0, which is just going to be 0, cosine of 0, which is 1, so 6 times 1, which is just going to be 6. So I'm going to try to do these values kind of quick. Okay, and then when I plug in pi over 4, this is going to be 6 cosine of 2 times pi over 4, which is going to be 6 cosine pi over 2, which is 6 times 0, which is 0. Okay, and then when I do pi over 2, so once again, so 6 cosine 2 times pi over 2, so that's going to be 6 cosine pi, which is 6 times -1, which is -6. Now what's going to happen is your pattern is going to continue. Every other value is going to be a 6, but the signs are going to alternate. And then every other value is going to be your zeros. So then if I just continue that pattern, it's going to be 0, +6, 0, -6, 0, and then back to +6. So every other value is going to be the length of the petal, and then the signs are going to alternate, and then every other value that's not the number, the length of the petal, is going to be 0. So when I graph the rows, it's going to be 6 in the direction of 0, then the pole, 6 in the direction of 3 pi over 2, but it's negative, so it's actually going to be negative 6 in the direction of pi over 2, which is the same as 6 in the direction of 3 pi over 2. And then we're going to go over here towards 6 in the direction of pi, and then we're going to go 6 in the direction of pi over 2. So I'm going to attempt, nope, nope. Oh no, that's not good. Well, like I said before, I'm drawing these by hand. It's not going to be perfect by any means. There we go. So when I look at my graph here, my really rough graph, we're going to have 1, 2, 3, 4. Well, according to this, it looks like I have 5 points, but I'm actually only going to have 4. I just can't draw. But yeah, we should only have... Oh, wait. Can I not draw? Oh, haha, no, I can't draw. Because my vertical circle should have a diameter of 6. No wonder it looks funky. There we go. Sorry, y'all. Okay, so 1, 2, 3, 4 points of intersection. There we go. I knew something looked a little funky. Okay, so we have these 3 points that we got algebraically, which are going to account for 1, 2, and 3 points. And then we already know that the pole's going to be a solution. Well, actually, we don't, because I didn't do the midline stuff. Well, we'll do that now. Sorry, I'm kind of all over the place on this one. So let's go ahead and check the pole. So once again, just as a recap, we're going to do the midline plus or minus the amplitude. So even though the period is different for this rows graph here, it doesn't change the fact that we're still going to do the midline plus or minus the amplitude to see if it's going to pass through the pole, which based on the graph, we can see it does. So if I do the rows equation, so if I do R1, well, I'm not adding anything over here or over here, so my midline is just going to be 0. So it's going to be 0 plus or minus 6 for actually both equations. So 0 plus or minus 6, which means we're going to go from negative 6 to positive 6 for both of these, which means 0 is included in both of those, which means the pole is going to be a solution. There we go. Now I think I got all my bases covered. Okay, sorry about my vertical circle. It was a little wonky. My rose is a little wilted, but it's fine. Okay, so my 4 points of intersection, when I look, we're going to have the points 3 in the direction of pi over 6. Listen. Okay, so 3 in the direction of pi over 6. We're also going to have 3 in the direction of 5 pi over 6. And then we're going to have, you can either put the points, you can say 6 in the direction pi over 2, or negative 6 in the direction 3 pi over 2. And then we're also going to have the pole. Go away. So these would be your solutions for this one. I think I said I wasn't going to do this one entirely, but, well, there you go. Merry Christmas. Okay, sorry, this video is probably going to be super long, but you know what? It's going to be informative. Okay, so number 12, I do want to do this one because this is going to be 2 rows equations. So now with this one, so we have 4 sine 3 theta and 4 cosine 3 theta. So with this one, we're going to have 2 roses. So I'm actually going to start by graphing this one. So when I do the graphing, I'm still going to do the same schematics as I did before. So I'm going to say this is R1 and then R2. Go away. So let's start with the period for R1. So that's going to be 2 pi over whatever my b value is, which is going to be 3. Now, if you notice, the b value on both of these is going to be 3. So really, I just need to do this part once, and I'll just set up the table for both. So the period is going to be 2 pi over b, which is 3, so 2 pi over 3. Now I need to do the spacing, which in this case, I'm going to do 2 pi over 3, and then I'm going to divide that by 4. Listen. So this is going to turn into 2 pi over 12, which means I'm going to do a table count by pi over 6. So I'm going to set up my tables. So I'm going to have R1 theta, and I'm going to do it, go away. And I'm going to do another table for R2 theta. So I'm going to count both of my tables by pi over 6. So starting at 0, so 0, pi over 6, 2 pi over 6, go away, which is going to be pi over 3, 3 pi over 6, which is going to be pi over 2, 4 pi over 6, which is 2 pi over 3, then 5 pi over 6, and then 6 pi over 6, which is pi. So generally what I will say for your tables, especially for the roses, I would just say go until pi. After that, it should start repeating. Should. But if you need more values, you can always add on more values. So I'll go ahead and add on the extra values just in case. So 7 pi over 6, 8 pi over 6, which is 4 pi over 3, and then 9 pi over 6, which is going to be 3 pi over 2. So I'll just add on those 3 extras just in case. We may or may not need them. Okay, so when I plug in, I'm going to do kind of the same idea over here. We're just going to do the first couple values, and then we're going to just use the pattern. Okay, so when I plug in for R1, so I'm going to plug in 0 for this first equation. So 4 sine 3 times 0, which is 0, sine of 0, which is 0, so 4 times 0, which is going to give me 0. So let's do this first rows in blue. Okay, so now if I plug in pi over 6, so 4 sine 3 times pi over 6, which is going to be 4 sine pi over 2, which is going to be 4 times 1, which is 4. So I can already kind of see my pattern here. So this is going to be 0, negative 4, 0, 4, 0, negative 4, 0, and 4. Okay, and then I'm going to go ahead and graph. So I'm going to do just one rows at a time. So 0, comma 0. Then I want 4 in the direction pi over 6, which is going to put me over here. Then back to the pole. And then I'm going to go negative 4 in the direction pi over 2, which is going to put me down towards 3 pi over 2, so down here. And then I'm going to go 4 in the direction 5 pi over 6, so that'll put me over here. So when I draw, it looks something kind of sort of like that. Close enough. Okay, so now let's look at the second rows. So I'll do this one in green. So we're going to look at the cosine rows. So I'm going to do 4 cosine 3 times 0, which is going to be 4 cosine 0, which is 4 times 1, which is going to start at 4. So if it starts at 4, then the next value is 0. Then it'll be negative 4, 0, 4, 0, negative 4, 0, 4, 0. Okay, so I'm going to start 4 in the direction of 0, which is going to be over here. And then I want back to the pole. So the pole is going to be a solution. I can already tell from that. And then I want to go negative 4 in the direction of pi over 3, which means I'm actually going to go towards 4 pi over 3. So that's going to be over here. And then I want to go 4 in the direction of 2 pi over 3, which is going to be over here. Okay, so my rows is going to go something like, terrible, something like that though. Okay, so when I look, I can see we are going to have a point of intersection at the pole. We're going to have a point of intersection over here in quadrant 1. We're going to have a point of intersection over here in quadrant 2. And then we should have another one over here in about quadrant 3. So we should have about 4 solutions. Okay, so what I'm going to do next, I did my graphing. I'm going to move that over here. Now I'm going to do the algebraic steps. So with the algebraic steps, now I'm going to set these equal. So 4 sine 3 theta is 4 cosine 3 theta. So I know based on the initial setup, I'm going to divide both of these equations by 4. So this is going to be sine 3 theta is equal to cosine 3 theta. Now the next part, you technically are not supposed to divide by a trig ratio, but what I'm going to do is I'm technically going to do an identity. Because if you remember back from your identities, I know that sine of x over cosine of x is going to be equal to tangent of x. So if they're the exact same thing on both sides, I know this means that we're going to look for tangent of x, which means if sine and cosine are the same thing, essentially I'm going to say that tangent has to equal to 1. Because these have to be the same thing in order for me to do tangent, and then I'm going to set them equal to 1. I hope that made sense. So essentially I'm going to do an identity. So I'm going to change, without dividing, I'm going to divide by cosine 3 theta, essentially. So I'm dividing both sides by cosine 3 theta without actually dividing, is what I'm trying to say, I guess. So when I divide, but not divide, that's going to turn into tangent 3 theta equal to 1. Okay, so what I'm going to do next is I'm going to do a little bit of a substitution. I'm going to ignore this 3 theta for a second. I'm just going to do tangent of theta, not 3, is equal to 1. Now in the unit circle, that's going to be equal to pi over 4 plus pi k. So now that I have the all possibles, I'm going to rewrite and include this 3 theta over here now. So this would be 3 theta equal to pi over 4 plus pi k. And then I'm going to divide everything by 3, which means I'm going to get theta is equal to pi over 12. That's 12. Plus pi over 3k. And then what I'm going to do next, now that I have all the possible theta values for the points of intersection, I'm just going to plug in integer values for my k value. So when I say integer values, I'm going to, you could use either negative k values or you could use positive k values. You could even use 0. But I'm actually going to start with a k value of 0. So when I do that, that means theta is going to equal to pi over 12 plus pi over 3, go away, times 0, which is just going to give me pi over 12. Okay, and then I'm going to do this for a few k values. After a while, or after a few values, hopefully you can see why we're going to stop after a few. So then we're going to do pi over 12 plus pi over 3 times 1. So when I do this, I'm going to get a common denominator, so pi over 12. And then that's going to be plus 4 pi over 12, which is going to be 5 pi over 12. So when I do a k value of 2, so that's going to give us a k value of 9 pi over 12, which is going to be 3 pi over 4. Okay, and then when I do another k value, so I'll do a k value of 3. So I'm going to try to skip some steps here, try to streamline some of this. That would be 13 pi over 12. Okay, so I'm actually going to stop at that k value. So once you get here, now you're actually going to plug in points to see what the coordinates are going to be. So I'm going to plug in pi over 12, 5 pi over 12, 3 pi over 4, 13 pi over 12, so on and so on. Now, once again, it's not going to matter which Rhodes equation you plug it into. It's going to work for either one. I have a proclivity towards sine, so I'm going to use sine. So I'm going to do R1 of pi over, is it pi over 12? Yes. Yes. Okay, so when I plug in, so that's going to be 4 sine of 3 times pi over 12. Listen. So 4 sine, and then that's going to be pi over 4. Sine pi over 4 is going to be root 2 over 2, so that's going to be 2 root 2. So this point is going to be 2 root 2 in the direction of pi over 12. Okay, so next I'm going to plug in, not 2. I'm going to plug in, was it 5 pi over 12? Go away. So 4 times sine of 3 times 5 pi over 12. So that's going to give me 4 times sine. So that'd be 15 pi over 12 divided by 3. That's 5 pi over 4. So that's going to be negative 2 root 2, since sine is negative in quadrant 3. So that's going to be negative 2 root 2 in the direction of 5 pi over 12. Okay, and then let's go ahead and do the next one, which is going to be 3 pi over 4. So I'm going to just save us some time. So when I do 3 pi over 4, that's going to give us 2 root 2. So that's going to give us the coordinate of 2 root 2 in the direction 3 pi over 4. Okay, and then I'm going to go ahead and do this last one too, but just to kind of show you what's going to happen. So when I do 13 pi over 12, what's going to happen is we're actually going to get a repeating point. So 13 pi over 12, when you plug this in, you are going to get no, it should be a negative, I believe. Hopefully. Kind of doing this in my head, but it should be, I believe, a negative. So you're going to get negative 2 root 2 in the direction of 13 pi over 12. Now, what I want you to notice is this point right here is the same as this point. So that's why you only need to do the first few, because the points are going to start repeating. So this is going to be the same as that point. Okay, so we're going to have these 3 points in addition to the pole as your solution there. If you keep finding more values, it's just going to repeat. Now over here, you can still do the midline plus or minus the amplitude if you want to check the pole over here. But because I did the tables over here, I'm not going to do the midline plus or minus the amplitude, because I know the pole's going to work. So my 4 points of intersection are going to be 2 root 2 in the direction of pi over 12, which that's going to be my point of intersection over here in quadrant 1. And then I've also got negative 2 root 2, and that's going to be in the direction of 5 pi over 12. So 5 pi over 12 is going to be this last little spoke over here in quadrant 1, but because it's negative, it's going to go the other direction, which means that's going to be this point down here in quadrant 3. And then for your other point over here on the petals, that's going to be 2 root 2 in the direction of 3 pi over 4. And that's going to account for your point that's going to be over here in quadrant 2. And then we've also got the pole, which I'm going to say is 0, 0. So those are your 4 points for the roses. Okay, now for the last 2 pages, so these are some challenge questions. I'm not going to do these. These problems themselves are going to take so long, so I'm just going to let you kind of read through and peruse. For my students, this would be a good Form C question, but I'll just kind of let you kind of look through it and see. Same idea down here on 14. These are some Form C questions. These are going to require some identities and some other kind of advanced concepts. So I will let you guys read through those. This video is already kind of long enough as it is. So make your choices. Have a good day.